Right. Thanks for being here last day. So this is joint work. Huh? Let me try using this. No. Click on this screen. Oh, this one. Okay, got it. Okay, thank you. There you go. Thanks, Laura. All right, so this is joint work with Chris Chambers, who is at Georgetown, and Nico Lambert, who is at USC. I thought I would start with a little bit of context, historical background that motivates this line of work. To some extent, what we're thinking about is, what is a preference? And so if you've been here in these days, you've heard lots of people talk about preferences, utility functions. People think about true preferences, non-true preferences, utilities, or the cardinal or the ordinal. Can we add them up? Can we compare one person's utility to another person's utility? So it's healthy to sometimes step back and think about what all this means. Sometimes you think, do you know your own preferences? Do you not know them? But if we think about preferences, it is a bit funny to imagine that preferences is something that you can take at face value. Is a preference something we carry in our minds? Do we have a ranking of all the options in our heads? Is it a hardwired assignment of numbers to alternatives in our brains? This is something that economists have thought about for many, many years. And early on, the answer was, no, that's not what we mean. So when we write down utility functions, we don't have in mind that people literally have utility functions. We only think that this is a convenient representation of their choice behavior. I have a quote for you from Paul Samuelson, who sort of summarized this. This was in 1938, but this debate had already been going on since the beginning of the 20th century. There was, first of all, that the word utility comes from this philosophical school of utilitarianism, which is an approach to ethics. And from utilitarianism, we got utility. And economists started talking about utility. Psychologists, quickly decided that utility didn't make sense, but economists were using it until Pareto and others came along and said, what really matters is just the ordinal content of this utility. Utility should only be ordinal, not cardinal. And Samuelson, in some sense, is summarizing these ideas, and he says, the discrediting of utility as a psychological concept robbed it of its only possible virtue as an explanation of human behavior in other than a circular sense. And then he says, why should one believe in the increasing rate of marginal substitution, which just means that preferences are convex, except insofar as it leads to the type of demand functions in the market which seems plausible. And this paper motivates, the real preference approach that Samuelson, proposed, and that we all use today. So Samuelson's approach is essentially empirical. So he says that preferences should be revealed by choices, and that the observed choices are the preferences. So when we write, I'm going to use the word squiggly to talk about that symbol. I don't know if you use another word, but I use squiggly. So x squiggly y means that x is chosen when the available choices are x and y. So from the menu, x and y, from the choice problem, x and y, you choose x means that that's exactly what x squiggly y means. Okay, so it's not something you have in your brains. It is, it's a statement about your behavior. Okay, so you should think that we are sort of this flesh and blood neural networks, and this black box is summarized by that squiggly symbol. Okay. Okay, so if that's all that matters, then presumably we need to take people and just measure their choices, take their choices, and that's it. That's how we capture who they are, what they do. So why would we care about preferences beyond what we can see people do? Well, because we can't observe everything. So if you have data on people's choices, presumably you don't observe them choose between everything, and you want to extrapolate, you want to predict, you want to make counterfactual choices. What would you choose if you were faced between these two things? Maybe I haven't seen you choose something, I have seen someone who is like you choose something, and then I want to make predictions about what you would choose. Or you're making policy recommendations, or making policy choices in a way that is benevolent. So I would like to make choices which were the ones you would make, if only you could make them. But I'm the policymaker, I'm making them for you. And so in that sense, I need to extrapolate or predict what your choices would be that I haven't observed. So that's essentially what I'm talking about in these papers, what we're talking about in these papers. So we're going to have a model. I'll show you the details of the model very soon, but there will be essentially two, if you want, agents in this model. So there will be Alice, who is running an experiment, a choice experiment, and Bob, who is a subject in this experiment. And the experiment will be simple. There will be a set X of universal possible alternatives or choices. Alice will present Bob with binary choice problems. So she will ask Bob, would you like X or would you like Y? And Bob would choose one of the two. And then rinse and repeat. So we'll get a data set, a finite data set of choices that Bob has made from pairs of alternatives. In the real preference theory, we talk about rationalization. The word rationalization is a preference that explains the choices. So a preference relation for which whenever Bob picked X, when X and Y was available, would rank X at least as high as Y is a rationalization, or if you want a weak rationalization, sometimes we say strong or strict rationalization when we insist that when X is picked, X must be strictly preferred. So this little difference makes actually a very big difference in the theory. So to summarize, there will be an experimenter, Alice, and a subject, Bob. The subject makes choices according to some preference relation, which is this black box model of Bob's behavior. Or if you want a utility, U star. But the only thing that matters, the only information that's relevant about the utility is the preference that it represents. That's sort of this old Paretian idea. The experiment conducts then a finite choice experiment of a size k. And then we have these rationalizations for each finite data. We find a rationalization that explains the choices, or one that explains as many choices as possible. And we want to understand how these things are related. So how is squiggly k, the rationalization, related to squiggly star, Bob's neural network, UK, the rationalization, and U star, which is the representation of Bob's squiggly. By the way, it's a big room, so maybe you guys are shy. I know some of you are not that shy, but do interrupt, ask questions. I do have this light in my, but if I step out here, I sort of see you. So if you do have questions, please raise your hand. Just to show you that this is interesting, let me show you or mention a negative result about how things can go wrong. So this is informal. This will make more sense once you see more details, but I think it sort of makes sense still if I explain it to you. So the following statement is true. Suppose Bob's preference is squiggly star. Okay? Arbitrary preference, it's continuous. Continuous means that it means that the graph of squiggly is closed. That's what it means. And it's an RD. So you're choosing among lotteries, or you're choosing among consumption bundles. And Bob is making choices which are consistent with this preference relation. And we have more and more data. We present Bob with more and more binary choice problems. Bob is making choices. And I'm being terrible at coming up with rationalizations, but I am coming up with rationalizations for each of these choices that explain perfectly Bob's choices. Okay? then no matter what Bob's original preferences are, I can be bad enough at finding rationalizations that these converge, and I will explain what convergence means soon, that these converge to complete indifference. Even though each rationalization is locally non-satiated. So if you don't know what locally non-satiated means, it means that you're never locally completely indifferent. Okay, so for every x, every neighborhood of x, there is y in the neighborhood which is strictly preferred to x. That's what locally non-satiated means. So I'm imposing some discipline on these rationalizations. I can't have indifference everywhere. In fact, I can never have even locally indifference. But despite that fact, I can be bad enough at finding the rationalization. They can be crazy enough off sample that I still get convergence to something that makes no sense, which is you're indifferent among everything. K is a sample size. So as you take the sample size, yeah.
Do you assume the choices are transitive?
These you can take it to be transitive, yes. So you can take squiggly star to be transitive, and each rationalizing K you can take it to be transitive as well. Yeah. Any other questions?
K was the set of alternatives, right?
K. So the set of alternatives is RD, and K is the size of the sample. It's a sample size. Here, if you want, you can do all pairwise comparisons of everything in the sample, and you can still get this conclusion. Yeah.
So, what's the convergence assumption here?
I'll show you in a minute. Yeah. Yeah, it's that's a very big issue in this whole exercise, and you will see why. I will pick what I pick, but yeah. Now, that's with finite many data. If I were already at the limit, there wouldn't be any problem. So that's what this theorem is saying. So again, suppose that the set of alternatives is RD, and there are two continuous preference relations, squiggly and squiggly star. Then if B is a dense subset, think of D as a countable dense subset, and these two preferences coincide on this countable dense subset, then they would have to be coincide everywhere. Okay? And this is just a simple consequence of continuity. So if we had already our infinite data that we got as the limit of this finite data, so we already had this countable dense set, then we would have this perfect identification. We couldn't get anything crazy. But by choosing things off sample with any finite data set, you can get things very wrong. So at a high level, then, the problem is to predict choices or make counterfactual choices on Bob's behalf, giving existence data on choices. And this is interesting when X is large relative to the data. So if the problem is small, then, of course, I can just ask you enough questions until I've exhausted all the universe of alternatives, and then there's nothing else to do. So in the paper, X will be infinite, and data is finite. And these two papers. I guess I didn't put the names of them, but if you want to look at them, send me an email, and I'll tell you which ones they are. One of them is published, the other one isn't. So the set of alternatives is X. So just today, think of X as a closed subset of RD. The preferences are going to be binary relations which are complete. So complete is the same as total or linear. It means that any two alternatives are comparable. So either X is ranked above Y, or rank is ranked above X, or both things true, in which case you're indifferent. Squiggly is continuous if it's closed as a subset of the product of X with itself. It's continuous if it's closed. And when I say preference, I'm going to mean a complete and continuous binary relation. Some of the results don't require transitivity. But if you want, you can think of this as being as all the preferences as being transitive. Okay, so if you want to capture what we typically think of irrational agents who make cyclic choices, some of these results allow you to talk about such agents because they don't require transitivity. Okay. And then the primitive of this model is then this pair X and P. P is a collection of preferences, and X is the choice, the set of choices. Yeah. What's the topology on preferences? What does it mean to say that one sequence of preferences converges to another? And the notion that we take is called the close convergence topology. I don't have a definition of this topology for you in these slides, but if you want to if you want to think of the simplest possible definition, imagine that X is compact. When X is compact and you regard the preferences as a subset of the product of X with itself, this coincides with the topology induced by the Hausdorff metric. So if you think of the Hausdorff metric between sets, then this is this metric induces the close convergence topology whenever X is compact. And you get this topology by compactifying X and using this idea. Well, there are different ways of characterizing it, but that is one of them. We did not come up with this way of modeling preferences. There's a very old idea in economics that people used many years ago when they talked about economies, where you want to talk about whether one economy is close to another economy. Involves thinking about whether agents' preferences are close to each other, and people use this topology for this. It is an incredibly convenient topology for the reason that's stated in this lemma. So if X is a closed subset of Rd, then the set of all continuous binary relations on X is compact. Okay, and it's a metrizable compact space. So this compactness is incredibly useful for what we're going to do. Okay, even though X itself is not necessarily compact, but we get a compact space of preferences, and that is very, very convenient for this whole exercise. Okay? So if you have questions about this topology, I can tell you more. There's a characterization of this topology in terms of behavioral closeness that also indicates it makes sense economically to use it, but yeah. Here's an example of the type of exercise. You can think of other examples, but here's one example of the type of exercise that we can think about. So if you have a set D of possible prices, and you have lotteries over these prices, X is the set of all lotteries over these prices, so then X is the simplex in Rd. And an expected utility preference is associated with a vector that assigns a number of utils to each price. Then for each such vector, I have a ranking of all the lotteries by their expected value. And that's one preferences. So to each von Neumann-Morgenstern utility, if you want, which coincides with a vector in Rd, I have a preference relation. And the set of all such preference relation is one example of a set P. Okay, so that's one example of a preference environment, an X, meaning the simplex, together with all the expected utility preferences. Okay. It's going to be very important to do something analogous to the assumption of local enunciation. And it's called local strictness. So here's the definition of being locally strict. So a preference is locally strict if for any x and y, whenever x is at least as good as y, for any neighborhood of x and y, I can find x prime and y prime which are strictly ranked. So I can break any indifference arbitrarily close by finding x prime and y prime which are strictly ranked. Okay? So this minimal notion of preferences being well behaved is going to be very important for this whole exercise. Okay, so remember, we have Bob participating in an experiment. These are choice experiment. These are binary choice experiment. You're going to give Bob a choice between X and Y. Bob is going to make a choice. Alice will get a finite data set of some size K. So sigma K consists of a collection of choice problem. And Alice is going to record the choices that Bobs make from each of these experiments. And the exercise is we're going to look at finite data, but large data. Okay? So we're going to take K to be larger and larger, and then Alice is going to keep a record of all Bob's choices. And she's going to have more and more data. A preference squiggly weakly rationalizes the data if whenever Z is chosen from problem xk, yk, then Z is at least as good as xk and at least as good as yk. So for the first result, I'm going to imagine a world in which Alice can perfectly rationalize all of Bob's choices. Then we'll deviate from this and we'll allow for data that can't be perfectly rationalized. But initially, we'll do the intellectual exercise of imagining that Alice can perfectly rationalize Bob's choices. Okay? And when I say rationalize, I'm going to mean weak rationalize in this sense, that she can find a preference which explains the choices in this sense. Okay. So I have this very big set of possible choices, RD, and I don't have any restrictions on the preferences right now. So I'm going to have to go and check everywhere. I'm going to have to go and check Bob. What do you choose between these two things over here, these two things over here? So in the limit, I'm going to have a data set which is dense in this space RD. Otherwise, I can't possibly hope to recover Bob's preferences. Okay? So I'm going to assume that in the limit, this set of choice problems that I present Bob with is dense in the space of possible alternatives. But of course, you know how to relax this. If you have more restrictions on preferences and that these preferences can be identified on a smaller set of alternatives, then you don't need this much. Okay, so I'm going to make this assumption to give you one result. But this assumption, you will know how to relax it. And in the papers, we do this in various special cases. We work out less demanding data restrictions. But at this level of generality, I need that the limit of these alternatives is dense in the set of alternatives. And moreover, I'm going to have to require something, which is what Jason was hinting at, which is when you have two problems, two alternatives, X and Y, that show up in the data, I'm going to have to present Bob with those two choices. So I have three assumptions. X is a closed subset of RD. Okay? This can be generalized if you're interested in generalizing it, because there are many models in economics which don't fall into this case. However, any kind of an actual empirical exercise, I think, would look like this. P is a closed set of locally strict preferences. There's a lot that goes into this being closed. So this seems like an innocent assumption, but actually this is a key assumption. The fact that I restrict attention to a set of possible preferences that I use to rationalize Bob's choices, which forms a closed set. So when I work out different applications, a lot of the work goes into proving that the set of preferences, space of preferences, is actually closed. For example, in R2, if you look at all the monotonic, continuous, and convex preferences, it's not a closed set of preferences. Okay? So if you look at the set of preferences we use in standard basic demand theory, when we teach micro 1, we have preferences which are monotonic, continuous, convex. That doesn't form a closed set of preferences. So that's a very substantial thing that needs to be checked. Expected utility preferences are closed. So the example I showed you before is one example where these things work out. But you often need some kind of Lipschitz conditions on utility functions, and you need some other restrictions to get a closed set of preferences. And finally, the sequence of experiments is exhaustive.
Question.
Yeah.
So in the bad example at the beginning of the talk,
yeah.
was it assumption 2 that wasn't satisfying?
Yes. Yeah. Yeah. You could choose preferences in a completely arbitrary way as long as log n associated, and then you get this completed. So so this theorem says that if these assumptions are satisfied, then no matter how I choose weakly rationalizing preferences, I will, in the limit, recover a preference relation. And if you want, you can take this to be a definition of Bob. So Bob is this black box that's generating choices. If I can always explain Bob choices, then in the limit, I will recover Bob. And this limit will be unique. So if I choose rationalizing preference in any other way, I will obtain the same limit as the number of data grows. And if you take Samuelson very, very seriously, you can think that this is sort of a definition of what preferences means. Preferences are what you get in the limit as you take many, large enough data from the subject's choices. Now, if there are no questions about this, I will change now to a different model in which I'm going to allow Bob to be random and to deviate from a preference if you want to make mistakes. So here, I'm going to borrow ideas from machine learning, in particular from old ideas in machine learning, pack learning, which I'm sure many people here know much better than I do. But I find this fascinating. And the idea is to think about preferences as a prediction or as a classification problem. Because a preference is a subset. So you can think of a preference as a hypothesis. Then, if you draw x and y, the question is x and y in squiggly or not? If you think about it that way, then you can apply standard ideas from pack learning to this problem. I'm going to make some choices, and I'm going to allow for Bob to make mistakes. So I'm going to change how Bob is assumed to make choices. Okay, so we still have this, Bob is still this flesh and blood neural network that's generating choices. But Bob doesn't always respect what the preferences tell him. He will deviate from it. Okay? And I'm also going to change how experiments are generated. I'm going to sample IID choice problems. Specifically, I'm going to obtain choice problems by drawing, according to distribution lambda, IID x and y's. I'm going to present Bob with x and y. But Bob may make a mistake. So this is a beautiful thing. I've never seen this before. So upon deciding on x and y, now I'm only going to use this thing, a subject which has preference squiggly will choose x over y with probability q, x and y. Okay? So q is a probability of choosing x over y when the preference is squiggly. And I'm going to make one assumption, which is that if x is strictly ranked above y, then this probability is greater than 1/2. Other than this, I'm going to make no assumptions other than technical measurability assumptions, so I can integrate things, on how Q and depends on X and Y. Yeah? I'm going to use an estimator, which we call Keynote minimizing estimator, sort of, because in spirit, this is, you're familiar with this Keynote rule in social choice. But the idea is very simple. You simply find a preference which explains as many choices as possible. That's all it is. OK? This is a very nice estimator because it is what we think of as model-free. I don't need to assume Q or to know what lambda is in order to compute this estimator. If you want to do something like maximum likelihood estimation, then I would need to actually have access to the distribution that is generating the data. I can compute this without access to that. I can just compute this knowing what the space of preferences are. Okay? It may be computationally challenging to compute it. That depends on P. Okay? So it could be, if it's a very rich space of preferences, it could be hard to compute this estimator. But that's a separate problem. In principle, I can compute it. Now, the point I want to emphasize is that I'm going to make assumptions which are parallel to the assumptions that I made in the Revere preference model and get a result. So I'm going to assume X is a closed subset of RD. P is a closed subset of strict preference. It's exactly the same preference, the same assumption I had before. And I have changed how the experiments are generated. So now I'm going to assume that lambda, the distribution I use to sample a choice problem, has full support. And this is crucial, that no indifference set, no indifference curve has positive probability. Okay? So we always struggle with indifferences in this type of exercise. So I'm going to assume, and you can imagine how to, if you have thin indifference curves, which you get from assumptions such as local association, then absolute continuity with respect to Lebesgue measure will give you this type of property. Then by using ideas from the theory of M estimators, you can obtain this result. So under these assumptions, if Bob preference is squiggly star, and squiggly K is obtained by matching as many choices as possible, by maximizing the number of choices that are matched in the data, then I get consistency. So this estimator will converge in probability to Bob's underlying preference. Oh, I'm missing. OK, yeah, this should come first. So the key to proving that is an identification lemma. If you're familiar with the theory of M estimators, if you think about maximum likelihood estimation, for each, what you need is that in the population, the true parameter has to be the unique maximum of the population likelihood. So the analogous phenomenon here is that under this population model, under lambda and Q, I can calculate the probability that if Bob's preference is squiggly, that in any randomly chosen X and Y is consistent with squiggly prime. And then the crucial identification lemma is that this object is uniquely maximized at the actual preference. So if squiggly prime differs from squiggly, then the probability of a randomly chosen X and Y being consistent with squiggly prime has to be strictly less than the squiggly. So basically, proving this is the main idea behind proving this theorem. Okay? Now, the next question is, this is consistency, but how much, so that consistency is in the limit as I get lots of data. How much data is enough? Yeah, Bobby.
So your results are very surprising to me because in physical learning theory, to achieve back learning, we usually need some finite dimensionality of the hypothesis class, finite dimension.
We will get that, yes.
Oh, okay.
Yes, I will get finite. So this is just consistency. I don't have any finite sample guarantee here. I don't have any approximation guarantee. I do have compactness of the parameter space because of this beautiful topology I have on preferences. So that compactness is enough to get this result. But to get a finite sample guarantee, I'm going to need finite VC dimension. So that's coming now. Yeah, thanks. Yeah. Exactly now, actually. OK, so as I mentioned before, I'm sure many of you know this much better than I do. But anyway, I'm going to use VC dimension of the class P. And for those of you who are like me until recently, here's the definition, or a quick definition of VC dimension. So the VC dimension of the class of preferences P is the largest cardinality of an experiment that can always be rationalized by P. Yeah? So it's a measure of how flexible the class P is, how prone it is to overfitting. So here's a story that that's for the economists in the room. So for the purposes of this, forget about Alice and Bob. I'm going to tell you a story about Alicia and Roberto. So Alicia is going to be a proponent of the theory P. And Roberto is going to question it. And they're going to be given a number k. Alicia is going to propose a choice experiment of size k. And remember, she's in favor of this theory. And Bob is against it. Bob is not trying, Roberto is not trying to, choose what his actual preferences are. He's trying to mess up Alicia. So he's going to try to choose make choices that are hard for Alicia to rationalize with her theory. Okay? So when k is small, Alicia can win. She can propose a pair of choices that Roberto, no matter how he fits it in, she can always explain it. But when k grows, this game goes in favor of Roberto. And the VC dimension is the largest k for which Alicia is guaranteed to win. OK? Yeah?
Make sure I've got the definition down pat.
Yeah.
For the set of transitive preferences, the VC dimension is 2?
No. For just transitive?
If we have an experiment of size 3 and Roberto gets to fill in the choices, he can say that A beats B, B beats C, and C beats A.
Right, but she's going to choose, A and B over here, and then B. This is RD, right? And B and C over here. Yeah, you're going to need to use RD somehow. For example, for linear preferences, this is just like linear classification, and then you get, then you get VC dimension is D. So for expected utility, you get VC dimension is D plus 1 or something. Yeah. If it's RD. Yeah. So this is the result that Bobby was hinting at, I think. So this is a standard pack learning result translated to our setting. And you will see what each of the sort of pieces that you need to work with in each special case comes in. So remember, I have this topology on the space of preferences, which is metrizable. So I'm going to take a metric for this topology. This is R. It's going to tell me how distant two preferences are. N is the sample size that guarantees a particular approximation. So it's the smallest n such that the sample k is at least n for every preference, so this is uniformity. So if every preference squiggly star that Bob can have, the probability that the rationalizing preference squiggly k is distance eta or less from squiggly star is at least 1 minus delta. So the n of eta delta is the sample size, is the guarantee on the sample size that tells me that I'm a particular distance away from the true preferences with high probability. Okay? So eta is the distance on preferences, and 1 minus delta is the probability. And I need this mu object that I talked about before. And this is sort of where I'm really just applying the pack learning, because this is really where the work goes into actually applying this result. So for now, I'm just going to copy the result off the shelf. So R of eta is the smallest difference in mu as long as the distance, the metric between mu and mu prime is at least eta. And so there's a lot hidden here. Okay, so you need to actually calculate this is a lot of work. So for now, I'm not going to calculate anything. I'm just going to call that object R. And then I get the next theorem, which tells me, gives me a bound on the sample complexity of this class of preferences. And it is the standard result you would get from pack learning. So, small VC dimension is good. Big delta helps me. And big R is also good. Okay? Any questions about this? So here's one example of how you apply this result to a specific environment. So this is the expected utility environment that I was talking about earlier. But remember, I had this assumption that you couldn't have locally strict preferences. So I certainly, that I must have locally strict preferences. So I certainly can't have indifference everywhere. So I'm going to let P be the set of all the non-constant expected utility preferences. This is a compact set, and you can see that because these von Neumann-Morgenstern utilities are vectors in RD. For them to be non-constant, it means that this vector is not a null vector. So I can normalize so that they lie on the sphere. And so it's a compact set of preferences. So that's a very nice parametric case in which the space of parameters I can just take to be all the von Neumann-Morgenstern indices which have norm 1. Okay. So in that case, I have these assumptions are satisfied because it is a closed subset of RD and the space of preferences is closed. And they're all locally strict. Now, in order to apply this result, I'm going to have to go and calculate this object that I mentioned before that I was told there's a lot hidden here in this guy. So in applying this result, the work lies in bounding this guy. So to do that, I'm going to need to control how quickly you approach 1/2 when x becomes very close to y. Bob makes mistakes. We're insisting that Bob is just more likely to choose x over y when x is more preferred to y. But how quickly does that converge to 1/2 when x becomes very close to y? And I'm going to control that by making an assumption. Actually, this only matters locally when x and y becomes close to each other. But never mind, you can make this globally. So I'm going to bound this probability below in a way that depends on the utility difference between X and Y. So I'm more likely to make a costly mistake than a non-costly mistake. And I'm just going to put a bound on how quickly this can go to 1/2. So this is an illustration of the kind. We have many more applications, but this is an illustration of the kind of work you need to do in actually applying this result. You need to add this type of assumptions in order to actually calculate this object R that is hidden in the paper. So anyway, so if you do that work, and I'm not going to show you the details, but this is what you get, and this is the type of dependence you get. You have a curse of the dimensionality there, which is unavoidable, but this is the type of sample complexity bound. We have many other examples: Cobb-Douglas, CS, Cara with subjective EU, intertemporal choice with discounted the Lipschitz bounded utility. We have many other examples of that kind. I have 8 minutes left. I can show you, let me just show you one more application. Unless there are questions about expected utilities. So I'll show you just one more example of how you apply this result. So so this is about monotone preferences, and just in RD. So think about, for example, choosing among consumption bundles in demand theory. So if you take K to be a compact subset of these choices, and fix AP that has finite VC dimension, okay? Choose your favorite one, I don't know, Cobb-Douglas or whatever you like. And moreover, make the assumption that it's identified on K. So as long as you have K, yeah, Johnny.
So, can I ask you about the previous?
Yeah.
So when you say big O,
Yeah.
how do L and M and N, all these go, how bad is it?
Good, yeah, I don't remember. Yeah, good question, yeah. It's hidden there, in there, yeah. Yeah, yeah, I should have put in there. It was probably just very ugly.
You learn from computer scientists that you say big O.
Yeah, this is, I'm getting there, he says. So this is, it's another, so this is just another application of the same type of idea with the big O. I'm gonna, so there's a little bit of a technical, I mean, these results, as you might imagine, once you need to bound this R guy, they get very technical. So here we have this theta relaxation of K that we need in order to actually calculate things. So I'm going to sample from the theta over 2K, K theta over 2 is the theta over 2 relaxation of K. So it's all the bundles which are distance, and that's the L2 distance, theta over 2 from K. And you're sampling uniformly from those. Then if you make Q dependent on the norm of the difference between X and Y, then you get this bound over here, where I have again hidden things such as the VC dimension of K, of P. And yeah, I have, okay. I'm going to, I could talk for another hour, which, but you guys are hungry. Just to summarize, let me mention, I have conclusions somewhere. I have results like this for utilities too. So these pictures are for utilities. I'm sorry they do them in ticks, but they are, okay, here's my conclusion. Just 1 minute summary of what happens with utilities. Utilities are more delicate than preferences. And the same type of theory can be developed for utilities, but they are more complicated. And you can construct examples where my assumptions on preferences hold. You can recover preferences in the limit, but you don't automatically recover utilities unless you're normalizing them in the right way and you're finding, you're sort of picking utilities from the right class. There is an analogous application of pack learning to recovering utilities. Again, the exercise is similar, where if you have two utilities that are different, you need to be able to calculate the probability that such differences are detected in the data, and then you have this computation of objects which are similar to the R of eta that are crucial in doing that. But that's essentially what the two papers do. They look at preference, they look at utilities, and they develop this theory for these two cases. The end, this whole framework is for binary choice. You can extend this to choice sets of size p, not just two, and then you have data which is generated by having Bob choose from many objects of that type. That is a simple extension that you can do. There is an extension to choosing for budgets. So there's a Berkeley student, Cristian Ugarte, who developed, extended this theory for choosing from budget, which is a very classical type of environment to look at. And in a sense, one thing that we like is that it provides sort of a unifying assumptions that work across these two environments. This deterministic, kind of naive preference approach in which you exactly rationalize everything, which is sort of the Samuelsonian type of model. And then this statistical model that relies on pack learning, and in which you recover preferences and utilities from choices which are subject to noise. We don't have any empirical applications in these papers, but we think that this is appealing for different empirical exercises. One type of applications that we think are kind of ripe for this type of theory are roll call data, because voting data is in Congress and other legislative bodies is very often binary. You're choosing yes or no on different bills. And there's a lot of work on recovering Congress preferences with this type of data. So we think that that's a kind of very sort of ideal application of this type of theory. But anyway, we haven't done it, but hopefully some will. And yeah, I think my time is up. So thank you.